Managing a modern metropolis effectively requires an operational tool far more capable than a traditional, static, three-dimensional CAD model. The international standard ISO/IEC 30173 defines the baseline for a true urban digital twin as physical virtual convergence, a living system that mirrors physical entities in real time. Urban planners are shifting towards prescriptive analytics, systems that calculate future outcomes, rather than descriptive data that only logs the past. The complexity is staggering. This intersection represents thousands of shifting variables, from vehicle density to pedestrian flow, all occurring simultaneously. Capturing this complexity requires engineering a complete architectural stack, connecting bedrock physical sensors directly to advanced machine learning layers. Attempting to transmit every raw data point from a major city to a central cloud would immediately overwhelm standard network infrastructure. To prevent this collapse, engineers use 4 operational layers: a hybrid network, edge ingestion, geometric integration, and predictive simulation. These layers operate sequentially. A failure at the network level corrupts the data before it reaches the predictive model, rendering the entire twin inaccurate. Success depends on matching specific hardware capabilities to the precise requirements of the urban data being captured. No single network can support a smart city. Planners must balance bandwidth, latency, and power consumption across thousands of different municipal assets. This technical matrix defines the protocol hierarchy. Mission-critical autonomous networks require 5G for sub-millisecond response times. Conversely, underground sensors transmit small packets via LoRaWAN, prioritizing massive coverage and battery life. Finally, legacy power plant hardware bridges into the twin using industrial protocols like OPC UA. This logical separation of protocols ensures that civilian internet traffic never interferes with emergency transit or utility signals. Transmitting millions of continuous sensor points directly to a central cloud creates intolerable latency and excessive operational costs. Edge nodes installed near the physical source process this data locally. These nodes filter out the noise and only forward specific anomalies or insights to the central cloud. For the final transmission, the system uses MQTT, a lightweight protocol for streaming IoT telemetry. It merges isolated transit, power, and water data into a single unified namespace, allowing analysis as one synchronized system. This edge-to-cloud continuum, backed by Apache Kafka for event streaming, ensures the virtual model remains perfectly aligned with physical reality. Sensory data requires spatial context. Engineers build a foundation using Building Information Modeling, or BIM, utilizing standards like CityGML to map the city's exact geometry. Mapping live data onto massive infrastructure, such as this steel bridge, allows for a level of oversight that physical inspections alone cannot match. In the Smart Bridge project, 500 physical strain gauges and accelerometers are mapped to their exact coordinates within the static 3D model. API layers then stream live structural readings directly onto those physical coordinates. This fusion of geometry and telemetry converts a static blueprint into a dynamic operational dashboard. The apex value of this technology is the ability to move from observing the present to predicting the future through prescriptive analytics. This table details specific machine learning models applied to diverse infrastructure. For bridge fatigue, deep learning autoencoders analyze vibration patterns to detect millimeter-scale cracks. In water networks, transsimilar models process pressure data to identify subterranean leaks, preventing water loss and road collapses. These algorithms also monitor massive energy grids, calculating transformer failure risks to prevent regional blackouts during extreme weather events. Combining physics-based modeling with deep learning allows cities to replace expensive, reactive repairs with proactive maintenance. Expanding these systems to encompass an entire metropolis creates an immense computational load. Building a city-wide twin as a single monolithic system results in extreme rigidity and severe processing bottlenecks. Instead, engineers use a federated digital twin architecture. This system relies on composable microservices, smaller, independent nodes that communicate across a unified network. This structure requires strict semantic interoperability. Standards like FIWARE and NGSILD ensure that data from different government agencies remains consistent and usable. Scaling a digital twin to a city-wide level requires decentralized processing held together by a standardized data language. Digitizing a city's physical assets changes the nature of cybersecurity. Because the twin is tied to operational hardware, a system breach creates direct physical risks for the public. This documentation outlines specific vulnerabilities, such as false data injection, which could allow an attacker to sabotage water pressure or energy grids. To counter these threats, cities adopt the NIST cybersecurity framework, utilizing zero-trust architectures, multi-factor authentication, and automated anomaly detection. When these systems are secured, they provide a massive economic return. Simulating construction projects within the twin reduces total project costs by up to 30% by catching engineering errors early. The urban digital twin is a city-wide operating system, translating urban chaos into a predictive science. By identifying these failure points before they manifest, this architecture provides a resilient, evidence-based approach to urban governance.